Hello. Some of you may have noticed that we didn't post a video from last Monday, and that's because we didn't work last Monday. I had other obligations. As it turns out, it was my 70th birthday, and we had a little get-together at my house. And anyway, so no working on pinball machines. And actually, we may not get to work on it again this Monday, but in the meantime, some of the off hours in the evening, I did get a little work done, and so I would like to talk to you guys about that. What you're seeing up on the screen here, which just went away for some reason. So what you're seeing up on the screen here is the board that I designed to interface a Bally pinball machine to a string of LED lights. This particular board was custom designed for this particular table, and we figured we could probably use it in other tables. As it turns out, in some cases we can, and in some cases we can't. We did use this in the 8-ball table. So 8-ball Deluxe, those are two different tables. And we've modified the 8-ball table as our guinea pig to make sure that we could do it before we went on to the 8-ball Deluxe, which is Mike's favorite machine. So I wanted to just talk a little bit about this board. I have talked about this board in previous videos, but because this board was designed for this machine, I wanted to go over it again, and I wanted to basically explain how this board works. So to start off with, let me just say that this big chip in here is not really a big chip. This is a STM32 blue pill board. It's got an STM32 processor on it, a bunch of I/O pins, USB connector, and all of that. And that is basically the brains behind doing all of the conversion. Now, this row of connectors here, and basically there's one set of connectors pointing up, one set of female connectors pointing down, and those allow you to plug into the existing microprocessor board on the Bally machine and then plug the cable that was plugged in there in here to continue it. So basically this inserts itself in the data stream and picks off 10 lines to monitor, and these resistors right here are just a line termination resistors to balance that line so that it doesn't get any ringing or anything like that. The rest of the lines, because there are other lines that are still used by the pinball machine, are just passed on through. The other connector right here, the other long connector, actually only has one pin on it, and that pin is driven by this transistor up here in the corner. It's actually an SCR, I shouldn't call it a transistor. This SCR up in the corner, and that drives the auxiliary relay board. So this particular machine has so many relays that the microprocessor board by Bally didn't have enough outputs for all the solenoids it needed, so they added an auxiliary board that basically switches, I think it's 3, might be more, relays to the signal line. So in one state, the microprocessor will activate one of the relays, and if you activate the expander board, it'll activate a different solenoid. So anyway, and the connector that goes out to that point would get plugged in here. The other things of note on this board is there's a power and ground input up here in the corner. We have 3 inputs for potentiometers in case we want to do intensity control or something like that. We'll probably only use one of those for now, but it is capable of handling 3 of them. There's an LED output, And this board was designed to support LEDs with and without a clock. So you got ground, power, data, and clock lines. We will only be using 3 of those because the LEDs we are using now are not clocked. And then up here are 12 jumpers that we can put in options. So if you jumper this jumper, it would activate a particular option. And one of the things we did with that on the 8-ball table was have an option for changing all of the GI bulbs to, say, green for St. Patrick's Day or something. So you just put a jumper on and all the lights turn green without any reprogramming of the computer. Let's see, I think that's about all that's on this board. There is a ground pin up in the corner here just to get chassis ground to the board. It is important that this board get a ground physically brought in because neither of these connectors actually have a ground wire on them, and therefore if you're trying to signal these lines, if you're trying to read these lines, the signals on there would have no reference if you didn't bring a ground in from the existing system. So this 5 volts in ground is a 5-volt power supply that we're adding, and this ground connects you up to the ground bus on the pinball machine. The only other little components on here, there is a 1.8K resistor here that is across the USB port on the STM32. This is a mod you need to do to make the STM32 use the USB connector correctly. And this little 2K resistor over here is just in series with this resistor. Okay, now that we've looked at that board, there's a few more things I want to show you, but before I do that, I want to take you over to the schematic and show you how this board interfaces with the Bally machine. Here is the schematic of this board, and right here are those 2 connectors, one male, one female connector on the bottom that interfaces with the Bally MPU. And as you can see, there are 10 lines that are attached. The rest of them don't go anywhere. And they are 4 address lines and 4 data lines, plus a master strobe and an auxiliary strobe. So on the Bally pinball machine, it uses these addresses and data lines to select light bulbs to turn on or not turn on, and if you don't turn it on, then it's off. Using SCRs, and it uses SCRs in an AC waveform, or at least a pulsating DC waveform, and when it does that, every half cycle the SCR turns back off. So they pulse it on, 120 milliseconds later it turns back off, they have to pulse it back on, comes back on, turns on, 120 milliseconds later it goes back off again, and they just keep on doing that over and over and over again for each of the lights that they want on. Now I should say these are each of the controlled lights. The non-controlled lights, the GI bulbs, are just always on. They just have power applied to them and they're just always on. So these are the bulbs that actually get manipulated. And let me bring you over and show you the schematic for the Bally MPU. So this is the microprocessor on the Bally machine. Sorry for the poor schematic. I've got this off of the ipdb.org pinball database, and this is the only schematic they have up there. It's the best I can do. We don't have one of our own, but this is good enough to work with. So if I zoom in here a little bit, so if you look here on J1, you will see the 4 address lines, the 4 data lines, and lamp strobe 1, which is the primary strobe, and lamp strobe 2, which is the alternate strobe. And those are the 10 lines that I need to get in order to convert what they were doing to drive my LED strings. The rest of the signals on this card need to continue on to where they were going, which is why there's the pass-through connector that passes that data on through. Now, another board of note is the old lamp driver boards. Now, the lamp driver boards can be completely eliminated, and these are the SCRs that drive the lights that I was just mentioning, and you can see there's quite a few of them. And because there are so many lights on this table, they had to add the auxiliary light driver board, and so these are the auxiliary light driver boards. So this board is strobed by the auxiliary strobe, or strobe 2, and these are strobed with the primary strobe, or strobe 1. But the thing of importance here is, if you look right here on pin 11 of J3, there's a line that says from auxiliary expander board. For some reason they decided to use one of the lines on the light driver board to activate the auxiliary solenoid expander board. So we have, since we're getting rid of this board, we need to rewire this auxiliary expander board to our new board, and we need to put an SCR on there in order to drive that. So going back to my board, you can see up here in the corner is an SCR. Now this SCR is driven through this 2K resistor out, and that activates the SCR, which then will activate the solenoid driver board through this connector. I think I said earlier that this board was designed explicitly for this table. As it turns out, other Bally tables that use solenoid expander boards put them on different pins on their boards. So I have a new board design that I'm looking at that only uses a couple of pins to take this signal off of here and take it over to wherever it needs to be used. So you won't plug the old connector in. You'll have to pick the wire out of it and put it into a littler connector to plug it onto the board. Also, you might notice up here that there's 2 holes for SCRs. This gate anode collector configuration is the way the Bally SCRs are constructed, but there are newer SCRs that are constructed with the gate in the middle, so I put both of those configurations on here, so regardless of which SCR you have to use, you'll be able to interface it there. I did want to mention something about the layout and how I use these lines. The 4 data lines, the 4 address lines, the main strobe, and the alt strobe all go into 5-volt tolerant pins on the STM32. An interesting fact, and it took me a long time to learn this, is these strobe lines latch the addresses into their lamp driver board, but the data does not occur at the same time as the addresses. It occurs slightly later, and because of that, it is asynchronous in relationship to these strobes. It could come anytime afterwards. So in order to use this and program it and catch all this data, I had to attach the 2 strobes and the 4 data lines all to external interrupts, so that whenever that line changed, I would get an interrupt and I would know that the data had changed and I had to do something with it. So the address gets latched in at strobe time, so I know which address I'm working with, and then the 4 data lines, which represent 4 different LEDs at that address, or 4 different light bulbs at that address, will come in sometime in the future, which would normally turn on an SCR. However, I need to capture that data and convert it into turning on an LED. So that was an interesting design problem I had to overcome. And so let me show you just a little bit of the code that handles this. It's actually just a tiny bit of code, and it works really, really well. So let me start off with the data. As I said, I have the 4 data lines attached to interrupts, and 4 bits makes basically a nibble. So I have a data accumulator that's going to accumulate the nibble. So if you think about the way the timing of this works, a strobe occurs, which latches the address in. Some time passes, and while that time is passing, some data bits occur, and then once that time has passed, another strobe occurs. So the occurrence of the strobe marks the end of data gathering for the previous address. So if you look at my data interrupts, they're just one line. All it does is if data 0 occurs, it ORs a 1 bit into the data accumulator. If data 1 occurs, it ORs a 2. If data 2 occurs, it ORs a 4. And if data 3 occurs, it ORs an 8. So if they all occur, they all get ORed, and you get a hexadecimal F in that nibble. If none of them occur, the data accumulator would be 0. So now the auxiliary strobe and the main strobe are pretty much identical routines except for where they store their data. So just looking at the main strobe, it takes whatever address the current address is, and whenever that strobe occurs, it needs to record what was happening before that. So the address from before already exists. The data accumulator, which was just being set by the data interrupts, gets stored in that array location. The address that caused the interrupt is read, and it is shifted over 6 bits. And because of where it occurs on the register lines, I need to shift it over to get it into the right-hand nibble, and then it's ANDed with an F to get rid of any other bits that are in there and store it in address. And that's it. So very quick, 4 instructions in the interrupt service routine, and it's done updating the address. Now, someplace else, the data that's being packed into this LED array will be read back out and displayed on the LED strings. But I got lots of time to do that, so I don't have to worry about it trying to do that here in the interrupt service routine. So that's all the coding I'm going to go over for now. I'll show you more bits and pieces of it as we go along with the building process. So here is the actual board. I soldered up, I spent about 3 hours putting this board together. The STM32 module, that blue module there, is, sorry for that auto-focusing, that blue module is plugged into a IC socket on the board, so it can be removed. We've got the connectors here with the female connector on the bottom. Let's see if there's some way, yeah, so you can see it there. So that's the female connector on the bottom that plugs into the microprocessor board, and then here's the pin that plugs into the connector that plugs into your cable that continues the signals on, and this other connector here on the side is where the auxiliary relay board cable gets plugged into. And I've got all the resistors, the connectors for the potentiometers, the jumpers, and the connector. Are you seeing any of this? I'm not watching. The connector where the LEDs plug in is right there. So anyway, we will bring this down to the shop the next time we're down there, and I'll show you how it gets installed. Well, thanks for watching. Hopefully we will get down to the shed sometime early in the week, and we'll be able to continue on with rebuilding the board, rebuilding the play field, and I can maybe bring this board down there and show you it from down there where it would go in the machine. So you guys have a great day. Thanks a lot for watching.